Okay, hi guys. So we're going to do a DC analysis of a common base transistor amplifier that is shown in the diagram on the left. So the question is asking, what is VR1? That's the voltage across this resistor R1 here. And what is VCB? That's the voltage between the collector and base of this NPN transistor. All right. All right. So first we need to okay, on the bottom left here, I just put down some common equations that you should already know. Okay, so let's start with first of all labeling our diagram. All right, so I'm going to use red to represent current. So there are, well, because we need to figure out what is the voltage across R1 and R2. Sorry, R1 and VCB. We need to know what kind of currents are flowing through the two loops. So let's just label our current first. So that the first one is IE, right? So this is the emitter. So the emitter current is flowing out that way. So that's the direction of IE. And then we have IB down here. And finally, we have IC in that direction. So IC is flowing into the NPN transistor. All right. Next, I'm just going to label the voltages. So I'm just going to use green to represent the voltages that we're interested in. Now, since IE is flowing right to left and therefore then going down through R1, since the current is going down, the voltage, the positive voltage is going to point up. All right, so I'm using green to represent the voltages that I eventually want to find an answer to. Down here for the V1, we have a voltage that is pointing that way. And then finally, we have a VBE. Since this is an NPN transistor, and since we are assuming the transistor is in forward active mode, so the VBE junction is going to be positive this way. All right, so that's your VBE junction. And similarly on the right, we have the voltage of V2 that is in that direction. And then since we have IC that is flowing right to left, which means you would have gone through going up R2. That means the voltage is pointing down. So the voltage, positive voltage for R2 is pointing down. And then for VCB, well, if you guys remember, for a transistor to function in the forward active region, the collector base junction must be in reverse order. So since this is an NPN, so NPN, so to reverse bias this, we put a positive voltage on the N side and a lower voltage on the base side. So therefore, VCB is going to be positive. Gonna put green here. So VCB is going to be positive that way. All right. So VCB is going to be positive that way. So now let's write some equations in order to figure out the various values. So the first thing we want to do is to figure out what's the equation on the left side, in the left loop. This is our left loop and this is our right loop. All right. Okay, so let's come over here. All right, so the first equation I'm going to write is just a KVL equation that links V1, VR1, and VBE. All right, so according to KVL, this is what the equation is going to look like. VR1 plus VBE. All right, so that's our first equation. And since we want to know what VR1 is, I mean, that's the question that's being asked. So straight away, we can rearrange this to be V1 minus VBE. All right. And since we have all the values that we need in order to work this out, V1 is just 2 volts. So it's going to be 2 minus 0.7. Okay, we're assuming 0.7 volts for a silicon transistor for VBE. All right, so that's going to end up as 1.3 volts. So now we have our first answer in terms of VR1. Okay. Now for VCB, well, VCB sits in this loop, and So we need to figure out, well, how do we figure out VCB? Well, because it's in this loop, we can figure out what is the equation for the right-hand loop, and then try to figure out whether if we can work out the voltage for VR2. All right, and then we can work out VCB because VCB is simply equal to V2 minus VR2. So let's write that equation down first. So the right-hand loop is going to be V2 is going to be equal to VCB plus VR2. VR2. All right, so that's the equation on the right-hand loop. All right. Okay. So what we want is, of course, VCB. So what we don't know is VR2. So how do we work out VR2? Okay, if you look at VR2, it needs IC because IC is the one that is going through R2 and then going into the collector terminal. So we need to work out what IC is. Well, how do we work out what IC is? Well, we're going to use these two equations. Yeah, we're going to use these two equations, combine them in order to work out what IC is. So I'm going to rewrite. I'm going to combine those two equations. So combining. All right. So combining those two equations. So we're going to have IE is equal to, well, we want to know what IC is, so therefore we're going to keep IC, all right, plus, now instead of IB, I'm going to substitute it with IC over beta, all right, IC over beta, all right, that's going to be what that is. So if I were to factor out IC, I'll get this, 1 plus 1 over beta, all right. Okay, so, and therefore I can write IC in terms of the equation that I just got, which is IE is going to be divided by all of this, all right? Yeah, it's going to be divided by all of that. Okay? Which I can simply I'll almost write the equation. Oh, sorry, I forgot. I need to figure out what IE is, first of all. And I can work out IE, because that's IE here, because IE actually flows through R1. So let me just, up here, add that. All right, so work out what IE is. Sorry, guys. All right, so VR1 is also equals to IE times R1, right? IE times R1. That's what VR1 is. So therefore, I can write 1.3 volts is equal to IE times 1 kilo ohm. 1 kilo ohm. All right. So therefore, I can write IE is simply 1.3 divided by 1 kilo ohm, which is going to be equal to 1.3 milliamps. All right. So now I got IE there. Okay, so now I can write here. So that's 1.3 milliamps up there, divided by 1 plus 1 over 80. All right. All right. So I did the calculation earlier. So you're going to get an IC that is equal to 1.28 milliamps. All right. Okay, so once we know what IC is, we can then work out. Yeah, so we know what IC is. That's the current going through there. So we can then work out the VR2. All right. So we can work out VR2. So VR2 is simply according to Ohm's law, V equals IR. So that's IE times R2. All right, which is equals to, sorry, not IE, IC. Okay, sorry, IC. All right, so our VR2 is just IC. This is IC. IC times R2. All right, so that's 1.28 milliamps multiplied by 5 kilo ohm. All right, and that's going to equal to all right, so that's 0.00128 times 5,000. That's going to equal 6.4. So this is 6.4 volts. All right. Okay, so now we know what VR2 is. We can then work out what VCB is based on this equation here, right? Okay. So we can therefore write VCB okay, is equal to V2 minus VR2. All right. Let me expand this a bit. Okay. So VCB is V2 minus VR2. So therefore, okay, VCB is going to be VCB is equal to V2, which is 15 volts. So it's going to be 15 volts minus VR2, which is 6.4. All right. So 0.6. So it becomes 8.6 volts. All right. So that's the answer. So that's the answer for this question. So we now have an answer for both VR1, which is, let me just maybe put some labeling here for the right hand loop. All right, so that's for the right hand loop. This is going to be for the left hand loop. All right. That's it. So we have our answer for VR1, which is here. And we also have an answer for VCB, which is here. All right, so hopefully you guys understand the process of getting this. Remember, the labeling of the arrows of voltages and currents are really, really important. You must get it right. If you get this part wrong, then you're going to make a lot of mistakes in here. All right? All right, thanks. See you guys in the next video.